Hello, everyone. My name is Gerald Zakwan, and I work with Roberto Valdez, and our topic is system design and machine learning. So there are several problem motivations, like constraint and serving models. We need to serve in low latency. We have limited resources. We receive millions of concurrent requests. We have a huge hyperparameter space. We have a diverse infrastructure requirements, and we also can take benefit from activity patterns for model training. And we have 4 papers here. The first one is practical lessons from predicting clicks on advertisement at Facebook. And the second one from Google, Google Vizier, a service for black box optimization. And the third one is applied machine learning at Facebook, a data center infrastructure perspective. And finally, from Microsoft, called Deep Learning Inference Service. And over to Roberto.
Perfect. Thank you, Geraldi. So yeah, the first paper we're going to talk about, it's called Practical Lessons from Predicting Click Ads on Facebook. So jumping into the problem motivation. So the thing is, click prediction systems are central to most online advertisement systems, right? And you also need a good system that guarantees relevant ads to be shown to clients. That's actually one of the promises of value of Facebook, right? And also you need to sort a large quantity of ads. You actually need to go from million of ads to maybe 4 or 5 that you need to show to your client, right? So you have a requirement of very low latency. Of course, this page has to function very fast. And also you need to use freshly generated data for the model. So these are the 2 requirements. So in the paper, they introduce a solution that is built on combining boosted decision trees for feature transformation and a probabilistic sparse linear classifier for prediction. Decision trees are a supervised feature encoding way of doing mapping the features. The trees learn the transformations through interactions, and also they provide a piecewise constant nonlinear mapping of the data. These are all really good features in terms of working with your features. So in terms of the combined boosted of the sparse linear classifier, sorry. And this model is built for obtaining the probability of a click. It's actually optimized for getting the maximum utility in terms of what you want to show to your user, and it can be easily trained online. So why do you need that data freshness in your prediction, right? Actually Facebook have measured how the bias of your predictions increment when your data gets sold. And this happens because, of course, the data distribution changes over time. So as if your data keeps getting old, your predictions keep getting bad. And that's actually what you can see in those graphs, right? So one possible solution you can do is actually just train instantly, train a model at each time every second. But of course, that's impractical. You need many resources. And of course, you introduce a lot of latency to your page or to your system. So what Facebook proposes in this paper is to break your model into parts, right? The boosted decision trees part is trained offline, sorry, and in a maybe 1 day span, right? And the linear classifier is trained on near real time. So in this way, you kind of get the best of both worlds. You have a complex part that is trained offline and a more simple part that is trained online. So you do this based on an architecture that's called the online data joiner, which is actually an architecture to build data on real time, right? You have the labels and you have the ads, the impressions, if a client clicked or not on a web page, and you actually build this data online and you feed it to the model online. And this data keeps generating, and the model keeps training online. And this is a constant way of doing things. But of course, you need to be very certain that your model works correctly, and you have to be very aware of system failures and many other things. Finally, the paper introduces a learning rate that actually is dependent on each feature. This is very important because for online learning, the learning rate is very important. And of course, this learning rate is the one that gives better results, according to this paper. And also the paper introduces, for feature selection, introduces 2 types of features. You have contextual features and you have historical features. Contextual features are more dependent on the context. So for example, in today, you would see election ads, maybe because of we're in an election. And you have historical features that depend more on the history of the user, what the user has clicked, right? And of course, not surprisingly, historical features are more predictive in terms of what the user is going to do. Okay, that's my paper. Going back to Jeremy.
Thank you, thank you, Roberto. And now we're going to discuss the second paper called Google Vizier, a service for black box optimization. And what is black box actually? So given function fx, it simply means that we can only evaluate any x on fx, but we cannot access directly the information within fx, like the gradients or the Hessian. And we need to find the best operating parameters to optimize our model. And then some concerns is when the evaluation is expensive, we need to actually efficiently search the parameter. We need to generate a sequence of x so that we can approach the global optimum as soon as possible. Otherwise, we just waste resources. And there are some algorithms that exist, like random search, grid search, simulated annealing, kinetic algorithm, and also Bayesian optimization. And this Bayesian optimization is the one that's used by Google. And there are some terms that are used throughout the paper. So the first one is trial. So trial is basically a list of parameter values, the x, one x, that leads to a single evaluation of fx. And the study is actually the set of trials, or like a parameter space that we want to try. And finally, the worker is the server that we use, typically provided by the client, to evaluate the pending trial. And this is the basic workflow. So you will have to input something called study configuration, which is the name, owner, and the permission of the study. And then the worker handle, or the server ID, or the process ID that is used to evaluate the trial. And then you will need to call the get suggestion, basically getting the trial to be evaluated, run the trial, and finally report back the results or saving the results. And this is the architecture. So here, the evaluation worker is the one that is provided by the client. So you create it yourself, and then you call the Vizier API, which basically connects you to several components. So the first one is called persistent database, which basically stores the state of all trials, pending or complete. And then we have the suggestion service, which polls the best trial to try at the moment. And then finally, the automated stopping service to determine whether or not one trial should be stopped early, given the characteristic of the trial. And this is the algorithm that Vizier used, called automated early stopping. There are two ways of doing that. The first one is by predicting the objective value of a trial given the previous trial. So it's like making some kind of regression. And then the first one is called median stopping rule. So basically it's the same, but then you need to create a running average until time step t, and then get the median of that running average. And then you compare it to the current objective value. If it's strictly worse, then you can just stop. And then is the second algorithm. So Vizier also supports transfer learning. So suppose we have tuned learning rate and regularization parameter for a certain system, and we have a similar system, but we have different data set. We can use Vizier transfer learning. So the idea is like you create a stack of regressors starting from the bottom to the top, and the bottom will be the very base training. So the one that has a lot of training data. Let's say it's like ImageNet. So you have millions of training data, and then the very top will be the one that is very niche. So for example, you have only animals data or building data, and then you go from the bottom, get the residuals, and feed the residuals to the top. And this is the algorithm playground. So if you want to create your own algorithm, you can also do that using this schema. So you have to custom two things here. So the get new suggestions basically means that you have to create the suggestion algorithm, what trial should be done first. And also the get early stopping. So you have to define your early stopping mechanism. And then you use that as your custom policy. And this is going to be interacting directly with the Vizier API. And it's very perfectly decoupled. So evaluation worker doesn't have to interact with your custom policy. And finally, the use cases. The first one is called Hypertune. So it's part of the Google Machine Cloud product that can be accessed by external developers. There's also automated A/B testing, in which, for example, you want to optimize the font, color, and spacing for your users' needs. And for some cases, like, for example, how should the search results return from Google Maps trade off relevance for distance from the user? So, for example, if you have, let's say, two factors, place distance and place relevancy, How do we trade off between those two factors to give the best results to the user? And finally, to address more complex problems in backlog optimization, such as invisible trials that cannot be done due to, let's say, very high learning rate. And finally, the trials that cannot be done due to resource limitation. And we can also mark, or we can manually override that trials. Okay, I think that's all. Over to Roberto.
Great. Thank you, Geraldi. Okay, so for my third paper, my second paper, sorry, what I did was looked at applied machine learning at Facebook, a data center infrastructure perspective. So jumping into the motivation of this paper, this paper describes the services that use machine learning at Facebook. This paper also describes the hardware and software infrastructure that supports machine learning at a global scale, and talks a little bit about the diverse architecture, the infrastructure requirements, and many other requirements that you can come up when you are implementing this type of systems. The key contribution of the paper are that machine learning is applied pervasively across nearly all services at Facebook. Facebook currently relies heavily on CPUs for inference and both CPUs and GPUs for training. But Facebook is constantly looking for prototypes and evaluating new hardware solutions for performance per watt improvement. The paper also introduces the fact that engineering and efficiency challenges, that there are energy engineering and efficiency challenges of moving this amount of data through the machine learning pipelines. And finally, the paper talks about making use of the diurnal activity patterns of the worldwide scale Facebook usage in Facebook, and making use of these downtimes that you get in order to improve training times. In order to use resources for training. Sorry. So the major services that are leveraging machine learning at Facebook, what you have are news feed writing algorithms. You have machine learning. People see stories that they need the most. You have search. You have ads. You also have anomaly detection. You have face recognition, you have high-level attributes and embeddings from images, which is very useful. You also have language translation and you have speech recognition. So you have this huge amount of services that are actually using machine learning. The paper also introduces the fact that Facebook uses machine learning as a service. So you can actually query a catalog and find feature generators for your model. If you want to build a model, you don't have to build it from scratch. You can actually use this feature store, and you can use predictors, or you can use trainers and evaluators that are currently and are custom built in order for you to work with your project, which is always good, not to have to reinvent the wheel. The paper also introduces the fact that at the time, Facebook is using two frameworks, using Café, that is optimized for performance, and using PyTorch, that is flexible for design. The paper talks about how you have to handle the trade-offs between having a very flexible system in where you can do a lot of research and come up with new algorithms, but of course you have to sacrifice performance, and on the other side you have frameworks that are really built on performance but have to sacrifice in terms of flexibility. The paper talks about the resource implications on machine learning. You have offline training is performed by CPUs and GPUs. You have the fact that distributed training, you usually think that you need a very specific type of interconnection, but Facebook deals with Ethernet-based networking, and it works really good. And also the paper talks about in online, you have these cascading classifiers that work at first with really big data, but really fast models, and then with really complicated models, but with really small data. And you have to work this, and maybe you have to use separate devices for it. And also, finally, the paper also introduces the fact that Facebook usually sometimes relies on mobile devices running on machine learning services in order to reduce latency. Finally, the paper talks about how to get data to the model and how you have this data workload and pending workload. And these are two different systems that need to be optimized separately because each one has its own characteristics and its own needs. So yeah, that's my paper, and going back to Geraldine now.
Thank you, Alberto. So we're going to discuss the last paper now. It's from Microsoft called Deep Learning Inference Service. So the purpose is basically to achieve ultra low latency for model inference. And it is used widely in Microsoft services, for example, the Bing search engine. And it is capable of handling 3 million inference calls per second. It serves over 10 of thousands model instances, and also deployed distributedly in 20 data centers worldwide. And it has utilized 3 concepts. So the first one is called intelligent model placement. Second one is called low latency model execution. And finally, the third one is efficient routing. And then this is the overview of the architecture. So here you have the model master, basically the orchestrator, the one that has the information of other components. And then we have model instances. So it's basically our model, DNN models deployed in a container. And then those deployed containers will be placed in a model server. And then this model server will be load and execute by other components. And finally, we have router. So it receives incoming requests, and it routes our request to the current best model server or to the suitable model server. And going to the first concept, intelligent model placement. So we basically are motivated by the fact that performance of different CNN models varies across hardware. We know that CNN typically are best to train on GPU, and RNN-based model are best to train on CPU or FPGA. And then how do we do that? How do Microsoft do that? So Model Master has a global view of every hardware and resources. And it also knows the estimated resource usage. So they run a prior validation test to estimate the resource. And then finally, for a model server to host a model instance, they have to meet 2 requirements. The first one, the hardware should be suitable. And then the second one, they have current available resources of holding more than 1 or more instances. And the next one, there's some kind of characteristic of this model placement. So the first characteristic is multi-tenant, meaning that you can host different models on one instance. Sorry, on one server, like CNN or RNN. And then it's also dynamic. So Model Master always monitor the availability of the resource in the runtime. And we also have to configure the hardware, so install the drivers, etc., etc. And also the machine will be pinging the hardware every 10 minutes to check the clock speed, to check the GPU health, etc., etc. And then going to the next concept called low latency model execution. So basically, we can optimize inference in 2 ways, model level or system level. And this paper talks about only system level. So first concept is called resource isolation. So basically, you want to isolate one instance from other instance to enforce 3 things. The first thing is called processor affinity. So for model critical data, the data should be placed near the processor cache. And then for the NUMA affinity means that you don't have to access across memories, cross-block memory. And then for memory restrictions, we need to be able to optimize such that we don't have to access the disk. So we always access the memory for fast inference. And then we also can take benefit from cache layers. And we also need to take into concern the server to model communication. For Linux, we use UDP. And for Windows-based, we use a so-called shared memory queue. And the final concept is called action routing. So there are certain patterns called frequent burst traffic, an explosion of requests in the span of a few milliseconds. And we handle that by using backup requests. So we basically ping, or we basically send the second request after the first one to make sure if the first one is not responded within a certain time, we still have a backup request. And there's still some issues with backup requests. So for example, let's say this is the scenario. We have an expected latency of 15 milliseconds, and then current 95% latency is at 10, and the average is at 8. So the issue is that when we, let's say, configure the backup request to be sent after 10 milliseconds, after the first request, it will obviously time out. But then if we pick up an earlier time, like 2 milliseconds, it will overload, like the system will receive a double workload. So we do cross-level cancellation. Basically, we pick an earlier time, like 2 milliseconds, but then we notify all the servers if the first request has been handled. So we can ignore the backup request. Okay, that's all. And over to Roberto.
So, okay, thank you very much. This is the end of our presentation. We have actually included observation and insights from our papers. These are observations written by us things that really caught our eye and really interest. And of course, because of time constraint, we are unable to actually go over each one of them and show you, but you are more than welcome to go and check them out. And if they interest you, we have also written some conclusions that we have that the paper has concluded, of course, has included, and we have actually went over and checked which are the most important ones, and we have selected and we have included. Also, you are more than welcome to check them out and maybe analyze them as well. Finally, we would just want to say to thank you for your time, for listening to us, and also to say to you, if you have any more questions or any things, please don't hesitate to contact us. We are free and you can actually send any questions you have. Thank you very much.